Hello maths fans, Dr. Tom Crawford here at the University of Oxford, and today I'm taking the American AP Calculus exam. The AP program allows students to take college level courses whilst they are still studying at high school. This means the AP exams are very popular in college applications and also for students who want to skip some of the introductory courses once they start college or university. There are 5 maths courses to choose from. 4 of them are in calculus and the last one is in statistics. Today I'm going to be taking the hardest calculus exam, which is called AP Calculus BC. The exam has a total length of 3 hours and 15 minutes. Section 1 covers 45 multiple choice questions and you have 1 hour and 45 minutes to answer all of those, before section 2, which looks at the free response questions, and there are 6 of those which must be completed in the remaining 90 minutes. Today I'll be doing part B of the free response section, which consists of 4 questions that I must answer in under 60 minutes and without the use of a graphical calculator. Okay, enough stalling, let's do this. Right, where are we going first? Starts on question 3, so I've skipped 1 and 2 because they were in the calculator part of section 2. Okay, so question 3 to begin. Very peculiar number question to start on, but nonetheless. Graph of a derivative. Okay, f's differentiable. We're told its value. Okay, let's write some of this stuff down. So f of 4 is equal to 3, so I know the value at a certain point. We've been given the graph of its derivative, which is going to be piecewise continuous. Nice. So I'm just going to copy that. So I always like to copy diagrams myself because I feel like it gives me a feel for the question. And it means I can actually annotate them here as well. So we're going round like so, this circular fashion. And it does say that is semicircular, and then we have a line segment going up to 6, 2, and then we're going to 7, 1. So I can see there, I don't know if this is going to help, but this line here is going to be y equals minus x because the gradient there is negative and we're going across 1 in x and down 1 in y. So maybe that helps. This is now going to be 0, 4. So we're going across 2 and we're going up 6. Okay, 6 over 2, so that's 3. So that's y equals 3x there for the derivative in that section. Again, don't know if these are going to help. We'll see. And then this is a semicircle, which makes it harder. So I'm not going to write the equation there, though I could actually work out where the center would be. The center would be at 0, 2. And so the equation of that circle would be, so it's centered on 0, 2, 2, 0. Getting my coordinates modeled. So that's 2, 0. And that's also 4, 0. Writing down all the wrong coordinates. Oh, so that's not 3x. Wow, this is a pretty interesting start to the question. At least I realized. Okay, let's check this again. I'm going to cross 1 and down. Yeah, so that's 4 on the x, 0 on the y. Yes. So this one is 2, 0 here. So the line now is going across 2 and up 2. So it's actually y equals x here. Right. Better. And then the circle, so that's x minus 2 squared plus y squared, because it's centered at 2, 0, equals the radius squared. So the radius is 2, so equals 4. Okay, not sure if any of this is going to help. I haven't even looked at the questions. But I have an understanding now, and this is the graph of f prime of x as x changes. All right, find f of 0 and f of 5. Okay. What do I know? I know that f prime of 0 from my diagram. I know that f prime of 0 is 0. What else do I know? So that would tell me that f of 0 is a constant. But would that tell me that actually? That might not necessarily tell me that. Okay, so no, that doesn't really help. Okay. So I've got to... This is, feels like quite a tough first question. Okay, f of 0 and f of 5. So I know that f prime of 5 as well. But is that going to help? So I don't know the general derivative though, which is an issue. Ooh, unless I use... Maybe I use areas. Because I can integrate f prime. Okay. I have a plan. I have a plan. So the idea is that I can't just integrate at these points because I need to know the general. If I had f prime of x, I could integrate and just sub in the values. But I don't have f prime of x. Or at least I don't have it very nicely. So I think what I want to do is, my idea is I can actually work out the area, and then I know the integral of f prime between those 2 points equals the area, and maybe I can get that in terms of the endpoints. I think this will work. Hopefully this will make sense when I start writing. Okay, so we're going to look at the area. Okay, so if I look at the area, right. So between the corner and 4, 0, so the semicircle, so its radius is 2. So that means semicircle area is pi times the radius squared. So that's 2 pi, I think. Okay, so I think the semicircle area is 2 pi. Pi times the radius squared would give me 4 pi, but it's half, so it's 2 pi. So that now means if I integrate f prime of x between 0 and 4, I should get minus 2 pi, he says. Minus 2 pi, I think. But then integrating it, so the left-hand side, so I put the negative there because it's below the axis, so I think it would come out as negative. But then the left-hand side I can integrate directly. So f prime of x integrates to give me f of x. So I've got f of x between 0 and 4, which is f of 4 minus f of 0. And I know f of 4, I think. Okay, this feels interesting. So I know f of 4, that's equal to 3. So maybe this is how you're going to do it, because why else would I have that value? But anyway, so 3 minus f of 0 is minus 2 pi. So therefore f of 0 is equal to, the right-hand side is equal to 3 plus 2 pi, I think. And then let's see if f of 5 I can do in a similar way. So yes, because I can use the triangle. So if I now look at the triangle, so I'm going here, let's write this different color. So if I go across to 5 here, and then I know this is going to be at 1, isn't it? So this is at 5, 1. So I've got 1, 1, because it's y equals x. So the triangle area is a half. So the triangle area is a half, but that's also equal to f prime of x integrated between 4 and 5. Yes. So if that is equal to a half, then that tells you that integrating up, that's f of 5 minus f of 4, which is f of 5 minus 3. Because again, I know the value of f of 4. I feel like this maybe was the way I'm going to do it, because I need that f of 4, which they randomly gave me. So that tells me that f of 5 is 3 plus a half. Right, so let's put these in boxes. So I think f of 5 is 3.5, and I think f of 0 is 3 plus 2 pi. All right, part B. What are we doing next? Find the x-coordinates of all points of inflection of the graph of f. Ooh. For between 0 and 7. Ooh. Huh. So a point of inflection is when you kind of come up, go flat, and then go up again. So if this is a point of inflection, what can I say is happening with respect to the gradient at that point? Because I have a graph of f prime, which is the gradient. This is my thought process. So we've got a positive gradient. Okay, so it's positive, and then it goes I wonder whether it has to go flat. I don't think it has to go flat to be a point of inflection. Depends on your definition. So point of inflection you may have come across when you have a function, you have an f of x, you solve when df by dx or f prime of x is equal to 0, and you work out your stationary points, and you look at the second derivative, and if it's positive then you have a minimum, if it's negative you have a maximum, and if it is 0 then you have a point of inflection. Well, potentially, I think, potentially have this point of inflection. So it's like the y equals x cubed graph through 0. Now, can you have, I think you can still have a point of inflection without necessarily, oh no. Interesting. So you would be going steep, and then you're kind of going to slow down, and then you're going to go steep again. So the one I've drawn, I think, always has a positive gradient, but it's steep, and then it goes flatter, and then it's steep. So I think I'm going to assume that I think, is still classified as a point of inflection. I'm going to go with that and hope that that is how the exam is defining this. I don't think it would be 0 derivative, because looking at that graph, I'm going to go with my first thought, and then we'll see. We'll see. All right, enough stalling. So it's positive, and then it goes, so it's like flatter. Okay, so it's always positive, but you're seeing a decrease. So it's a decrease in gradient followed by an increase. And if you had the negative version of it, so y equals minus x cubed, for example, it's negative, it goes flatter. Okay, so it's the gradient flattens out and then goes steeper. Okay, so it's whenever I think it's going to be whenever the gradient goes flatter and then steepens, is my guess. Okay, so where does that happen on my graph? Well, let's draw my graph again. So semicircle bit, flat bit, and down. Right, and then this is at 4, this is at 6, and this is at 7. Okay, so what's happening to the gradient? So we start off, we have a negative gradient, right? So it's negative, and it's getting more and more negative. So we have so here, this is the maximum negative gradient. So this is the most negative value of f prime. So the maximum negative gradient is its steepest negative, and then it starts to increase, but the gradient doesn't increase. Sorry, the gradient value increases but remains negative. So that means it's flattening, becoming less negative, yeah. So it flattens. So then this bit, it sort of flattens. It flattens, it does pass through 0, and then it becomes positive. So it's flattening, but it's going from negative to positive, so that's going to be a minimum. So I think there's a minimum at 4, which is obviously not the question, but I think there's a minimum at 4. So let's just write that. So I think there's a min here. So I think there's an inflection point then at 2, by that logic, because you're negative, you're starting to flatten out a little bit like my picture, and then you're remaining flat, and then you're becoming positive. Oh. But it stays negative, so it's flat, it steepens, and then it goes flat. Yeah. Flat, steepens, flat. Wait. Increasingly negative, increasingly negative. I think it's 2. I think it's x equals 2. Okay, so I think inflection x equals 2, because there's the change in the steepness. Yeah, because it's increasing to steepness and it starts to slow down. Right, since gradient becomes more negative as x tends to 2 minus, so tends to 2 from the left, and then becomes less negative beyond it. Past x equals 2. Yeah, that makes sense, I think. Of all points of inflection, okay, so I got to 4, I think 4 is the minimum, and obviously not a point of inflection. Then, and this, okay, so I think my original thought process of an inflection point just being that kind of wiggle, I think that's correct. You don't have to go flat. Otherwise, I don't think there would be any. And then we're increasing, so we then have a positive constant gradient. Okay, so f prime is increasing. Sorry, it's not constant. We have f prime increasing gradient, yes. And then what's happening at 6? And then so this is then the maximum positive gradient. Max positive gradient up here. And then it starts to become less steep. So that's the positive inflection. Okay. Same at, when's that happening? 6. Same at x equals 6, but now positive gradient throughout. Okay, yeah. So it's those points where you turn around. You're in the positive or negative bit, and it's there where you like loop round in the graph of the gradient. Could potentially lead to the inflection point, yes. And that would fit with my cubic example, which I always keep in my head for the classic canonical inflection point example. All right, I think, is that it? That is it, and I think my answer has been justified. Right, part C. Let g be the function, God, it's another function. G of x is equal to f of x minus x, okay? And what intervals, if any, is g decreasing? Okay, so I want to know when is g decreasing is basically the question. Okay, show the analysis to your answer. Right. So given I have a graph for f prime, and then g prime is, when is g prime decreasing? Well, that's whenever, so decreasing function means negative gradient. So that's equivalent to saying that g prime is less than 0. So I need to calculate g prime. So g prime of x, and that's in terms of f prime, nice, is equal to f prime of x minus 1. So I want, so therefore g decreasing when g prime is negative, but that's equivalent to f prime being less than 1. All right, so if I look at my graph, so it's less than 1 between 0 and 5. So that's for x belonging to 0 and 5. And then, yep, that would be true. 0 would be included, for sure. And then it's bigger than 1, it's bigger than 1, it's bigger than 1. So be it. Yes. Because it's not less than 1 between 6 and 7, 5 and 7. Yeah. Okay, is that it? Huh. All right, well that was a bit shorter, like that one. Part D. For the function g defined in part C, find the absolute minimum value on this interval. Okay, absolute minimum of g. Okay, so again, let's just start with what I know. I know that g of x is f of x minus x. And I can see how it's linked to part C now. Clever. So, by part C, g is decreasing for x between 0 and 5. So if g is decreasing along that entire range, it's going to start at a value. So g of 0 is some fixed value. We have g of 0. I actually know what g of 0 is. So g of 0 is, of course, f of 0, which I worked out, I think was 2 pi plus 3 minus 0. So that's just 2 pi plus 3. Okay, so the value doesn't matter, but let's just go with it. So g of 0 is this value, 2 pi plus 3. G then decreases all the way until x is 5. Okay, so it then decreases until, so therefore I think the minimum is at x equals 5. So g of 5 is the minimum. Do I need to know that value? Find the absolute minimum value, sure. Okay, so I think that means work it out, but let's just check. So it has a fixed value at 0, decreases until you get to 5, and then from 5, then it becomes an increasing function because its derivative is positive. Yes, so it's going to start to increase again, so we don't care. Okay, so g5 is minimum. Now, I know what that is. And g5 is, of course, f5 minus 5. I worked out f5. It was 3.5, wasn't it? So that was 3.5 minus 5, which is minus 1.5, minus 3 over 2. Okay, so I think the minimum, absolute minimum value of g, I think, is going to be minus 3 over 2. Oh, and that's it. Okay, end of question 3. How many marks was that? I didn't even... Does it tell me? Okay, it doesn't seem to tell me, unless it's on the cover that I didn't read. It doesn't seem to tell me how many marks. Okay, maybe the marks seem, I guess we'll find out when I mark it later. All right, well, that was 3, A, B, C, D. All right, pretty nice, pretty nice. Well, let's move on then to question 4. An ice sculpture melts in such a way that it can be modelled as a cone that maintains a conical shape. Ice sculptures, classic. Do you have many? Surely you don't have that many ice sculptures in the US. If this was maybe like, I don't know, a Norwegian or Swedish or Finnish exam, but are there Canadian? Are there really that many ice sculptures in the US? Anyway, conical ice sculpture, and it's going to maintain the shape of a cone as it decreases. Okay, probably going to need to know the volume of a cone than I. The radius of the base is given by a twice differentiable function. Okay, feels like this is important, so let's write this down. So question 4. So we have a cone, which we're interested in. So we have a cone, and we know that the radius of the cone is twice differentiable. Okay. So they wouldn't be telling me that unless I'm going to need it somewhere. RFT is measured in centimeters, t days, values in the table. Great. Of r prime, the rate of change of the radius. Okay. For part A, approximate r double prime of 8.5 using the average rate of change of r prime over the interval t between 7 and 10. Show the computations and indicate units. Okay, so I think what it's getting me to do here then is so using the average rate of change, so that's basically saying, I think, is saying use a linear function between those 2 points. So between 7 and 10, so I think then it's saying we're going to assume that that is equal to, so r of 8.5 is halfway between 7 and 10, right? So if I take, yeah, I think that'll work. So if I take r prime of 10, the later one, minus the earlier one, which is r prime of 7, and then divide by 10 minus 7, I think. So let me just plot this visually for a moment. So I'm saying, what am I saying? I'm saying that I've got t here, and I've got 7, and I've got 10, and then I'm going to plot r prime, and it has some value. Of course, they're negative. Value, what have we got? We got minus 4.4 and minus 3.8. Okay, so let's just put it down here. So we got minus 4.4, minus 3.8, and 4.4 is at 7. So we're like here, and then we go to here. So it's basically saying the rate of change at this point is then, it's kind of like a rise over run. Okay, that seems sensible, I think. Sure. So r prime of 10 is minus 3.8. Minus minus becomes a plus, and that one is 4.4 divided by 3. So that's going to give me 4.4 minus 3.8 is 0.6 divided by 3 is 0.2. Share the computations, great. Indicate the units. So I've done r prime on top, which is centimeters per day, divided by time, which is day. So it's centimeters per day per day. cm per day per day. That classic, well-used unit. Centimeters per day per day. All right, B. Okay, and I could do that because it's twice differentiable. Maybe that's why it's told me that. Is there a time t for which, r prime of t equals minus 6? Okay, r prime of t equals minus 6. Right, so in the table we've got, okay, so I know that r prime of 0 equals minus 6.1. I know that r prime of 3 is minus 5. So it's clearly, to go from minus 6.1 to minus 5, it has to pass through minus 6. And can I argue that it's provided it's continuous? Can I argue it's continuous? Yes, because I know that so r prime is differentiable because r double prime, r is twice, I knew I was going to need it, r is twice differentiable, which means r prime is differentiable. And being differentiable implies continuity. So differentiability implies continuity. So it implies continuous. So if r prime is continuous and it starts at minus 6.1 and goes to minus 5, it has to pass through minus 6. So therefore passes through minus 6 by, if you want to be completely correct and rigorous, by the intermediate value theorem. So that tells you a continuous function, if you have 2 points and the function is continuous, the intermediate value theorem says it meets or reaches all of those points between the 2 ends, as it must if it's continuous. It's one of those where, like, I remember, like, when I'm teaching this, it's like, it feels really obvious that this would be true for anything that's continuous, but you kind of have to formally state it, and that formal statement is called the intermediate value theorem. So I don't know if I need that, but maybe. I don't know how rigorous AP calculus is. I guess I'll find out. It does say justify. So the answer is yes. Therefore passes through that. So yes is the answer. Okay, it's going well. Part C. What are we doing now? use a Wright-Riemann sum. God, it's been a while since I've done Riemann sums. So you write Riemann sum with 4 sub-intervals indicated in the table, Jesus, to approximate the value of this. Okay. So I do actually teach second year numerical analysis, but we don't actually use Riemann sums when we're approximating integrals. We use other, better methods, like quadrature, for example. And we do also derive Simpson's rule, the trapezium rule, that kind of stuff using the approximating polynomials. Anyway, none of that's going to help me here. So what do I know? Right, Riemann. So Riemann sum is where you're like doing step functions. So I'm going to plot this and sort of do it like a bar chart, I think, if I remember correctly, is how you do Riemann sums. So we want to know the integral from 0 to 12 of r prime of t dt. And what do we know? We know that this is going to be very negative, isn't it? Because they're all negative. So if this is t, this is r prime of t. Okay, so we know that at 0 it's minus 6.1. So let's write that one in over here. And then we've got minus 5. We've got minus 4.4. Definitely not to scale. Minus 3.8. And minus 3.5. Okay. Right, so we have these various points that we care about. Definitely not to scale. And then we're going 0 to 3, and we're at minus 6.1. Okay, so then at 3, okay, so we are here, and then at 3, we are here, and then at 7, which is a little bit wider, and then 10, and then 12. Okay, so at 7, we're at minus 4.4, which is like here. 10, we're at minus 3.8, and 12, we're at minus 3.5. Okay, right Riemann sum. So I think, I'm not entirely sure, but I think that means I'm going to use the right-hand limit. So for this first sort of block, it's like drawing a bar chart. So between 0 and 3, I could draw my rectangle to either be of height 6.1, minus 6.1, or height minus 5. And I think the right-hand value of it, of the range 0 to 3, the right-hand value would mean taking the value at t equals 3. So I think it's telling me to do it like this. I think. So I think then my first sort of approximation then is to say that is width 3 times minus 5, which is like the height of the thing. So then if I sort of fill that in, so then the next section will be at the height of 7, the next one is at the height of 10, and the next one is this one. So that would be the right, left would be starting at 6.1 and then go 5, 4.4, 3.8. If I were to do left, but it does say right, and I think, fingers crossed, this is how you do the right one. So 3 times minus 5, and then we've got a width of 4, so plus 4 times the width there is minus 4.4, the height, plus 3 for the width, and that height is minus 3.8, and then finally plus a width of 2, and that's minus 3.5. I think. And it is going to be negative because obviously it's an area, but it's below the axis, so I expect a negative value, which is what this will be. So that's good, right. So that's minus 15 plus, no, minus 16 will be 17.6. Minus 3.8 times 3 is 11. No, can't be 11.5, 11.4? 11.4? Yes, minus 11.4. And then minus 3.5 times 2, minus 7. Okay, so that's minus 22 for 15 and the 7. 17.6, something like 18 minus 29. So that's minus 51. Does it want units again? No. Okay. Assuming I've remembered correctly what right Riemann sum means, I think I'm happy with minus 51. Okay, right, which means part D. The height of the cone decreases at a rate of 2 centimeters per day. Okay, so I know, what do I know? So the height, h prime of t, is 2. No, minus 2, because it's decreasing at a rate of 2. Because I know r prime in the table, so I'm guessing the height is decreasing and it's just constant. Seems to be constant. Okay. Because r prime, of course, as we saw, was changing. All right. At time t equals 3, the radius. Okay, so we know that r of 3 is 100. And we know that h of 3, I'm assuming it's going to ask me to solve a differential equation. H of 3 then is 50. Okay. Find the rate of change of the volume of the cone with respect to time at t equals 3. And I'm given, okay, so I'm told the volume is 1/3 pi r squared h. Glad it told me that. Possibly would have forgotten. No, I think I knew that one because it's 1/3 of a cylinder. Okay, and it wants you to work out the rate of change of the volume with respect to time at. Okay, so I think I want, let's just make a note. I think I want v prime of t at t equals 3. I believe. So differentiate. So if that's v, then v prime of t is 2/3 pi, r times dr by dt times h from the chain rule, and then I have to do a product because h is also time dependent. So plus 1/3 pi r squared h prime of t. Yes, maybe. And I want to know this at t equals 3. Okay, so v prime of 3 therefore is 2/3 pi. Radius at 3 is 100. R prime of 3 is in my table. Yes, it is. Minus 5. H of 3 is 50. Amazing. Plus 1/3 pi. Radius squared, so it's 100 squared, which is 10,000. Yikes. Yes, and then H prime is a consistent minus 2. So I can get a very negative answer, which I think sounds correct. Yes, because the volume is decreasing. Fabulous. Okay, so I think the answer they want then is v prime of 3 is... okay, minus 250, so it's 2/3 pi times, put in a bracket, minus 250 with an extra 2 zeros, so 25,000 with a minus, and then we're going to do another minus, and we've already got the 2, and we've got the 1/3, and we've got the pi, so minus 10,000. Okay, so I think it's minus 70,000 pi divided by 3. 70,000 over 3, which does not, I think, divide by 3. 70,000 pi, is that right? Minus 35,000 times 2 is minus 70,000 over 3 pi. That's a lot. In cubic centimeters per day, so that's centimeters cubed per day. All right, well, I'm going with it. That's my answer. And is that it? All right, woo, another one done. Let's move on to question 5. 2 down, 2 to go. What have you got for me? Question number 5. Figures 1 and 2 shown above illustrate some regions, short, in the first quadrant. Right, well, let's draw those. Obviously, all about redrawing my graphs. So what have we got? Going between, nice hyperbolic functions here. So we've got 1 over x between 1 and 5. Okay, and that'll carry on. Great, and we're going to call that one r. Short, and then we've got w, which is 1 over x squared. Okay. So that's gonna decrease a bit faster. Whoops, very bad drawing. Let's redo that one, I think. 1 over x squared, okay. And that's from 3 onwards. Okay, so 3, and then this is going to be w, and this one's now 1 over x squared. Okay, interesting. W be that one. Perfect, and that's unbounded, so the w one's going to infinity, okay. So this is very Gabriel's horn. So I've actually used to use this question in the undergraduate admissions interviews here at Oxford, and I made a video about this on my channel, this channel, if you're watching this, along with Steve from Black Pen Red Pen, another excellent maths YouTube channel that you should totally check out if you haven't already. So I asked him this question and we went through kind of how I would set up Gabriel's horn, which is the volume of revolution around the x-axis of these curves, basically, 1 over x curve. So we're doing 1 over x squared here, and I'm going to guess we're probably going to do something similar, considering it's talking about this kind of infinite, unbounded area. Once you rotate it, you're going to get a horn shape, which is infinite, and that's referred to as Gabriel's horn. Anyway, little aside, and obviously go watch the video that I made about that. But what am I asked to do here? Find the region R. So, straightforward. So part A, I want to know the region R, so that's just the integral from 1 to 5 of 1 over x dx. The integral of 1 over x is log of x, so that's just ln of x between 5 and 1, which is just ln 5 because log of 1 is 0. Perfect. Okay, region R is the base of a solid. Sure. For the solid, at each x, the cross-section perpendicular to the x-axis is a rectangle. Perpendicular. So it's, okay. Very oddly worded question. I think the idea is it's going to come out of the page. Okay. Because it's the base. You've got region R, and it's coming out of the page, so it's like a 3D shape, right? And it has an area of x e to the x over 5. Find the volume of the solid. So I think I can just treat that as a density. So it's a very peculiarly worded question, but I think the idea is you've kind of got this solid coming out of the page, and we're told like the area of it as it comes out, and then we need to take that thing, like that slice. Yeah, we're going to take that slice and then integrate across from 1 to 5. I'm pretty sure is what's happening. So if I take the density function to be this x e to the x over 5, and I integrate that between 1 and 5, I think that's going to work. Meh. I have no other ideas as to what it could be asking me to do. So I think the volume I want, therefore, is just literally the integral from 1 to 5 of the function they've given me. So again, I'm treating this as a density is how I'm thinking about it. So if I do that as x e to the x over 5, right, and I can integrate that. It's some integration by parts, isn't it? Right, so let's use a different color. So I want u to be equal to x, so then du is 1. And then I want, which means dv is e to the x over 5. U dv, yes. So then that means that v is the integral of that. So if I had 5e to the x over 5, differentiate that, you bring down a fifth, they cancel. Great. So using the integration by parts formula, so using IBP, that's going to tell me now what? It's going to tell me that the volume V is equal to UV in the bracket, so 5x e to the x over 5 between 5 and 1, minus the integral of V du, according to the formula. So that's now just 5e to the x over 5 dx between 1 and 5. Right. So I can just about squeeze this in. So that's going to be 5x e to the x over 5 between those two limits, minus So you integrate that again, you're going to get an extra factor of 5. So minus 25 e to the x over 5 between 5 and 1. Right. So combining the two things into a single evaluation. Yes. I think that works. Great. Because I've done the integral and then put the limits in. Right, okay. So what is that? We're going to have to rewrite this out. What was it? 5x e to the x over 5. So volume is 5x e to the x over 5 minus 25 e to the x over 5. And I want to do this between 5 and 1. I think. Let's double check I've correctly copied that out. 5x e to the x over 5 minus 25 e to the x over 5 between 5 and 1. Yes. All right. So that is, subbing in, we get 25e, x over 5, yep, minus 25e. Okay. So that's 0 minus, when you sub in the 1, so minus 5e to the 1/5 minus 25 e to the 1/5. Okay, so the first bracket is 0, and then it's then minus, and then we've got 5 minus 25 of that, so that becomes a plus 20 e to the 1/5. So I think the volume is 20 e to the power of 1/5. Wild. Okay, find the volume of the solid. Sure, why not? Okay, C. Find the volume of the solid generated. Here it is. When the unbounded region W is revolved around the axis. Volume of revolution. Could have written this question. All right, so volume of revolution is given by, there's a formula for this, so it's like pi r squared, and then you integrate. So it's equal to pi. The radius is given by the function, so that's 1 over x squared, is playing the role of the radius, but you have to square it because it's pi r squared. And then you integrate dx, which is going to be from 3 to infinity. Okay, fab. So can I integrate that? Yes, I can integrate that. So it's equal to pi, the integral from 3 to infinity of 1 over x to the 4th dx, which is equal to pi. And then in the brackets, we've now got, what have we got? Minus, so it's going to be x to the minus 4. So if I have x to the minus 3, you bring that down, so minus 1/3, x to the minus 3, I think, between 0 and infinity. Let's just check by differentiating. So x to the minus 3, bring the minus 3 down, becomes a plus, the 3's cancel, and reduced by 1 gets x minus 4. Okay. It's not between 0 and infinity, Tom, it's between 3 and infinity. Get that correct first. Suddenly changing my limits partway through the question. Okay, so then that's just as x tends to infinity, I should probably write this properly, shouldn't I? As x tends to infinity, minus 1/3 1 over x cubed will tend to 0. So I'll get nothing from that. So therefore the volume in this instance is pi. 0 minus minus becomes a plus, so 1/3 and then 1 over 3 cubed, which is 27. So I think, very similar to Gabriel's horn, the answer for Gabriel's horn in the video I did was pi, but this is going to be pi over 81. So 1/81th of the value of pi, I think, is the volume. And woo! And that is question 5 done. Right, last one, question 6. It almost feels too easy. Famous last words. Question 6. Maybe I just picked the easy section, who knows? The function f is defined by the following power, very fun, power series. Okay, so, wait. Oh no. Thought we had the sine series for a moment there, but it doesn't have the factorials. Okay, interesting. Okay, anyway, f of x is given by x minus x cubed over 3 plus x to the 5 over 5 plus minus even ... and then minus 1 to the n, right? X to the 2n plus 1, so we're doing odd powers of x, and we divide by the power of x. Yeah, great. And then we carry on. Cool. Okay, so it's like the odd powers of the x to the n over n with alternating. Okay, cool. Yep. For all, if I read that one, for all real numbers x for which the series converges, using the ratio. Whilst I've done the ratio test, using the ratio test, find the interval of convergence of the power series of f. Justify your answer. Okay, so I believe the ratio test states, what does it state? You have to do like one term divided by the other and show which one do you need to be bigger. The old one should be bigger because the terms need to get smaller. So the ratio test means we need to consider the an over an plus 1. No, would that be, hang on. So if that's going to tend to 0, that would mean an plus 1 is bigger. No, so I want an plus 1 over an, I think. Is that going to, yes, that's going to be right. Okay, so I want an plus 1 over an, yes. Yes, because then, okay. So consider an plus 1 over an modulus. If this tends to 0, we have convergence, I think. Again, it's been a while since I've done the ratio test, but I think this is the idea. So if you put the next term above the previous one, so you want the previous one to be bigger, which means you're going to tend to 0, which means the terms are getting smaller as you progress. And that, I believe, allows you to argue convergence, I think. Okay, well, let's try it anyway. Okay, this is 0, we have convergence. So, what would that be here? So, an, so let's call this, define this to be r. So the ratio in this question then is minus 1 to the n plus 1, x to the 2n plus 3, yes, divided by 2n plus 3. And then on the bottom we want an, so that's now minus 1 to the n, x to the 2n plus 1, and then on the top we're going to get the 2n plus 1. Right, and we take the modulus of that whole thing. So, minus 1, so I get a minus on the top, ultimately we don't care. I'm left with an x squared on the top, and then I've got 2n plus 1 over 2n plus 3. So, as n increases, what can I say? 2n plus 1 over 2n plus 3. So as n tends to infinity, you have to take the limit. Right, it tends to 0 as n tends to infinity. It's the bit I was missing. I couldn't quite remember it all. I think that's the correct bit. So as this will tend to x squared, tend to the modulus of x squared as n tends to infinity. So I need, wait, is that right? Yes. And I need this, does it have to tend to 0? Does it need to be less than 1? Maybe it's less than 1. Because that's not going to tend to 0 unless x is 0. So I'm going to go back and modify my ratio test and say, I don't need this to tend to 0 if this is less than 1 as n tends to infinity. As you can tell, I'm rusty. If this is less than 1 as n tends to infinity, I think we can argue convergence. So it tends to that, and so we can say that r, which equals the modulus of x squared, is less than 1 whenever the modulus of x is less than 1, i.e. X is strictly between 1 and minus 1. Classic. That feels sensible. And it can't, okay, so it can't be my original thought tending to 0, because that would mean that x would have to be 0, which is a problem. Yes. Okay, going with it. Okay, now what does it want me to do? It wants me to show that something. Okay, well, let's calculate the something. Show that f of a half minus a half is less than 1 over 10. Well, what is f of a half? Start there. So f of a half is x a half minus a half cubed times a third, okay, plus a half to the power of 5 times a fifth minus dot 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 dot. Okay, so f of a half, so what can I say? So therefore rearranging f, so I see now why it's f of a half minus a half, because that's that first term. So f of a half minus a half is, with a modulus, is equal to, the modulus of minus, what's the next term? Half cubed? Half cubed is an 8, 1/24th. 1 over 24. Plus the next term, which is 1 over 2 to the 5. Oh gosh, what's 1 over 2 to the 5? 1 over 2 to the 5 is 32, and then times 5 over 1 over 160 minus dot dot dot. Where does the 10th come from? Because I would argue, so I know that, so the next term here, so the next term which we subtract is smaller than 1 over 160. So we're never going to get smaller than that minus 1 over 24. So I think, and that pattern will continue. So I think, therefore, f of a half minus a half, I think, is actually less than, with the modulus, is actually going to be less than 1 over 24. So where does the 1/10 come from? Because I think it's less than the modulus of x cubed over 3, x cubed, yeah, it's definitely that. So if it's less than 1 over 24, that's less than 1 over 10. 10, so done. Is that true though? I'm pretty convinced. So the idea is you're taking the first term, you're subtracting it, and then I'm saying the function minus the first term must always, because it's alternating, so this is because alternating, since alternating series. Because it's alternating and the terms get smaller and smaller and smaller. So you're always like, sure, you're adding something next and then you subtract something, but the thing you subtract is smaller than the thing you added. So you can never get back down to that minus 1 over 24 is basically what's happening. So you can never get, it's going to sort of like be, I don't know, it's going to be something around 1 over 24-ish. Yeah. So I think it's less than 1 over 24, which technically is less than 1 over 10. I'm going to go with that. It's true, but I'm a little confused because I was hoping 1 over 10 would pop out when I subbed in those numbers. Maybe I've missed something, but anyway, let's move on. Part C. Write the first 4 non-zero terms and the general term for an infinite series that represents f prime. Term by term differentiation, baby. Don't know if I need to write that, but I'm going to go with it. So if I know what f of x is, so f of x is, was it what, the first 4 terms? 4 non-zero, right. So if f of x is x minus x cubed over 3, plus, so it gives me them all very helpfully, minus x to the 7 over 7, plus dot dot dot, plus the general term, minus 1 to the n, x to the 2n plus 1, divided by 2n plus 1. So, plus dot dot dot. Therefore, term by term differentiation, because it converges. So I'm going to say term by term differentiation is valid. differentiation is allowed when it converges uniformly. Allowed for mod x less than 1 since convergence is uniform. Again, don't know how much rigor I'm supposed to do, but we will write it nonetheless. So I can basically do that because it's an infinite sum. If it was a finite sum, you can just differentiate each term. It's like a polynomial. But because it's infinite, you have to be a little bit careful. And you can do it when you have uniform convergence, that kind of interchanging. And I'm pretty sure that what I've shown here is uniform convergence, he says. Again, rusty. So convergence is uniform, I think, so that allows me to do that. So therefore, f prime of x, first few terms are going to be 1 minus x squared plus x to the 4 minus x to the 6 plus ... plus. It's going to still be minus 1 to the n, and then it's going to be x to the 2n. So we now get the even powers with alternating. Even powers where we alternate between plus and minus. Great, plus ... So that's the first 4 terms and the general term. Right, yes. Great. Use the result from part C to find the value of f prime of 1/6. Okay, let's see if I can squeeze it in. So f prime of 1/6 is what? Is 1 minus 1/6 squared plus 1/6 to the 4th minus 1/6 to the 6th, etc., 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 plus ... Okay. So what are we doing here? That is times minus 1/6, times minus 1/6 all squared. Yes. So we're multiplying by minus 1/6 squared, and then we multiply by minus 1/6 common ratio. Yay! Okay. I think it's a geometric series. Let's just check. So, right. So I believe then, just to write this out formally, that f prime of 1/6 is 1 minus 1/6 squared plus 1/6 to the 4th minus ... So we've got a common ratio. So this is then times minus 1/6 squared times minus 1/6 squared, etc. So I can say it's a geometric series. The common ratio r is minus 1 over 36, which is minus 1/6 all squared. And the first term, a, so this is the common ratio, just in case you don't use r and a in the States. And a, the first term is 1. And this is infinite, so the sum of infinite geometric series is given by a over 1 minus r. So here that's 1 over 1 plus 1/36. So 37 over 36 on the bottom. So it's equal to 36 out of 37. So that's the infinite sum, and this is okay. This converges. Convergences. This converges. Can't spell or write. This converges for the modulus of r less than 1. And here the modulus of minus 1/6 is minus 1 over 36 even, is less than 1, so okay. And I'm going to put a smiley face because we are done. That felt a little too easy. That genuinely felt quite pleasant. That was a very enjoyable hour spent solving some reasonably straightforward calculus questions. I don't really know what to make of this, because most of these exams that I've done, or at least the ones I've done recently, I feel like have been exceptionally challenging, or there's been something that I've forgotten, like circle theorems. But that was just some very nice, it was like calculus, it was some integrals, it was some volume of revolution stuff, a little bit of series and convergence. Maybe I'm now beginning to formulate a hypothesis in my head. Maybe the fact that this is college level, so university level, introductory university level, and the fact that I teach university level first year calculus to my first year students here in Oxford. Maybe that's why it feels a little bit easy, because this is like the first problem set that I would do with my first year students. So maybe that's why it's almost like I'm almost at the level that I'm now teaching at, or like the basic level that I'm now teaching at. And maybe that's why it felt more familiar and therefore a little bit more straightforward. Of course, this is all assuming I've actually done okay. And who knows until I mark it. So before I dig myself into an even deeper hole by claiming this was all totally chill and totally fine, I think we'd better do some marking. So I should have mentioned at the beginning, the exam that I've just done, or part of the exam that I've just completed, is from the 2022 paper, the AP Calculus BC exam paper from 2022. So as usual, I will link the full paper in the video description so you can download it and have a go for yourself, have a go at the other questions, maybe using your own graphical calculator. And I will also put the mark scheme, which I have in front of me. I'll also put that in the video description. So again, you can have a go yourself and you can mark it. And I will put the mark scheme for the whole paper, or as much of it as I can find, again in that video description box. But for now, let's actually mark my solutions to part B in the free response section from that 2022 paper. So question 3, this was the function or the graph of the derivative of the function. And it asked me to find f of 0 and f of 5. We now have marks. Okay, so this is out of 9. Question 3 is out of 9. Didn't tell me that in the question. I don't know if this is standard, but as always, I've never looked at anything to do with this particular qualification. Don't know the syllabus, no idea of the course structure or even the exam structure, beyond picking this particular section because I didn't need a calculator. Anyway, so 9 marks. Part A is supposedly worth 3. So it did want me to do areas, perfect. And 3 plus 2 pi, yes. Remember getting that, good. And 7 over 2, 3.5. All right, so that's 3 out of 3 for the part A. Very good start. Part B, x coordinates for the points of inflection. What are we saying over here? We're saying it could have an inflection at x equals 2 and x equals 6. Did I say x equals 2 and x equals 6? Woo! Justification, because f prime changes from decreasing to increasing and from increasing to decreasing. Ooh. So I'm saying the gradient becomes more negative there and then it becomes less negative. So it's f prime changes from increasing to decreasing. Increasing to decreasing, decreasing to... I mean, I think I've given a good enough justification. Are there any specific things I can say? Let's see. To earn the second point, reading into the details, our response must use correct reasoning based on the graph of f prime. So citing x equals 2 and 6 as the locations of local extrema. Yes, so I've written them as maximum positive, maximum negative. I think that should be okay then. I didn't talk about f double prime. I didn't talk about f. Cannot be earned. No, I didn't do that. I think I've done it. So I did discuss, there we go. Correct reasoning, discussing the signs of the slopes of the graph of f prime. I think I deserve those 2 marks. I'm going to do it, right? 2 out of 2. Okay. Probably could have said that at the beginning, but I'm trying to be slightly critical of myself. Anyway, right, is that it? Yes, part C. What did we have to do for part C? They want me to... oh yeah, this new function. On what intervals is g decreasing? Show the analysis. Right, g decreases between 0 and 5. Woo! And interval with reason because g prime is less than 0. Amazing. 2 out of 2. 2 out of 2. Whoops. I'm writing. Already written 2 out of 2 for part D. What did I even do for part D? Let's just check. Preempting. The function g, find the absolute minimum value. Right. What is it meant to be? Minus 3 over 2. So I got it correct. I got that correct. Justify your answer. What do I need? Because it's saying g is continuous, work out g prime, the absolute minimum before it then starts to increase. Here we go. G prime changes from decreasing to increasing. Yes, so it's decreasing because then it starts to increase. Yes. I feel like I maybe didn't write that much, but I definitely explained to you all, so I'm claiming 2 out of 2. All right, good start. 9 out of 9 for that first one then. The next one, question 4 is also 9 points. I'm going to assume that maybe all of these are 9 points. I guess we will find out, but the first two definitely are. What do I have to do here? Approximate r double prime of 8.5 and give the units. So I did that. Yes, I did that, and I got 0.2 centimeters per day. Boom, 2 out of 2. Is there a time when it's, this whole continuity thing, what's it saying? The answer is yes. I knew it'd be twice differentiable. So r prime is differentiable, which means continuous. Fabulous, therefore, they mention intermediate value theorem. I almost didn't write that. Felt like a little bit too much, but yeah, sweet, 2 out of 2. It's going well. Let's look at part, Riemann sum. Not sure about this one. Use a right Riemann sum. Minus 51! Was definitely not convinced I'd got that one. Form of right Riemann sum, which was that one, times 4, times 3, times 2. There we go. Amazing, 2 out of 2. Seems stingy to only give me 2. That one I wasn't sure about. Fab, and then the last part, part D, the volume. Oh, this is the weird answer. Minus 70,000 over 3 times pi. Minus 70,000 over 3 times pi. Brilliant. So I got the answer, and product rule, chain rule. Okay, 3 out of 3. So far, so good. Okay, question 5. What was this? This was the revolution stuff. Yep, liked this one. Obviously out of 9. Find the area, do the integral, get log 5. That is what I got. Okay, 2 out of 2. 2 out of 2. Part B. Oh, this weird solid one. Right. Write down the integral. Good, so that's a good start. I did write that down. I used integration by parts. I totally forgot the plus c because you don't need it. So you only need the plus c mark scheme when you don't have limits. But I have limits, so plus c shouldn't be there. Just going to throw that out there. So it gets 20e to the 1/5, right? Did I get that? Did I get 20e to the 1/5? I got 20e to the 1/5, yes. And that was a good 4 marks for that one. Which means I'm going to guess 3 for the last one. 3 for the last one. Volume is pi r squared, yes. Do the antiderivative, yes. Do the answer, pi over 81, right. The first point, the second point is earned for that one. To earn the answer point, our response must use the correct limit notation. I cannot include arithmetic with infinity. But I can definitely write, I'm claiming I can write infinity as a limit. It's fine. I think that's fine. I didn't write, it says you can't write 1 over infinity cubed. I never wrote that. I did say it would tend to 0, however. So I think that's fine. And I'm going to give myself those final 3. Last one. So that's 27 out of 27 so far. And then I'm going to assume this is going to be out of the last 9 marks. Question 6. This is where I was a bit rusty. My convergence stuff, been a while since I did first year analysis. I teach second year complex analysis, but we don't do much ratio test. Right, ratio test. So, what does it say? Sets up the ratio, which is the limit as n goes to infinity of the n plus 1 term over the n term. So I set that up. Good. So I get a point for that. I need modulus of x squared less than 1. I said that. And I said, therefore, the series converges when x between -1 and 1. Oh. I might have lost marks. Shit. Ah. Oh, really? Really? It considers both endpoints. Oh, no. I didn't do the endpoints. When x is -1, the series is alternating whose terms decrease, so therefore converges by the alternating series test, and the same for 1. Oh, I forgot the endpoints. Oh no, 2 out of 4. Forgot endpoints. Rookie error right there. I told you I was rusty. My confidence was misplaced. I was rusty on that one. So you were supposed to check the endpoints and use the alternating series test. I did not even, thought didn't come into my mind to do that. So I accept I've lost 2 marks there. Damn it. Oh, it was all going so well. All right, part B. Hopefully the rest was okay. Right, part B. Ooh, this one was weird. Show that, right, uses the second term. Yes. So the alternating series error bound, f the half distance from half by the absolute value of the second term because it alternates. Yes. So they got this. That's really weird because we get this. So you can basically show that it's less than 1 over 24. But I was thrown because the question said show that it's less than 1 over 10. So I was doubting using this method was okay. Turns out the mark scheme says do exactly what I did and then realize 1 over 24 is definitely smaller than 1 over 10. That's naughty. I don't like that. But I did at least get my 2 out of 2. So that is good because it's definitely less than that. Yes. Okay. Right. Derivative. Didn't need to mention convergence or uniform or term-by-term differentiation. It says right out the first 4 terms, which I've got. 1 minus x squared plus, yes. General term, -1 to the n, x to the 2m. Boom, 2 out of 2. And then the last bit, use that result. Geometric series with a equals 1 and r equals -1 over 36. Pretty sure I wrote exactly those 2 things. And then get 36 over 37. So that's the last 3. So that was 7 out of 9. Bloody endpoints. So that gives me a total mark then. Total mark. So I got 4 marks on question 3, 9 out of 9 on question 4, 9 out of 9 on question 5, and I dropped 2 because I forgot the endpoints. Lesson to all of you watching, check your endpoints when you're doing radius of convergence. I know I will in future. So that's 34 out of 36. Okay, fine. Silly mistake, but as I say, thought didn't even cross my head. But the rest of it, my confidence was correct. Yeah, that was, as I say, it felt nice, it felt pleasant to do. I enjoyed the entire experience. That was, compared to the other exams, it was harder than the SAT, because I think the SAT, comparing this to the other American exam I've sat, the SAT is a much lower level, and you could definitely tell these were more involved questions. Definitely felt a lot easier though than, I'd even say felt easier than A-level. Probably harder than GCSE, even though I did worse than GCSE, circle theorems. I'd say harder than GCSE because it was more advanced ideas. That first question in particular, and then the infinity and the limits. I mean, it's stuff I'm familiar with, but it's more advanced topics. So I think maybe similar to A-level. I'm going to claim similar to A-level, maybe a little bit. I found it easier than further maths. I think I found it easier than the arbiter, definitely easier than the step paper. So I think it kind of sits like between, is it harder than A-level? Okay, let's say it's harder than A-level. I think it sits just a little bit harder than A-level maths. And again, I think the topics are more advanced, like the stuff at the end there about convergence, that's definitely a university or a college level topic, as this whole exam is designed to be, like introduction to college level maths. But for me, sitting it, this felt easier because it's stuff I personally am more familiar with. So on my like tier list of how I find the exams, I think this is going to slot in as tiny bit harder than A-level maths, but easier than everything below that. So there you have it. I've scored 34 out of 36, which I think is a very respectable score. Bloody M points. And that was on the non-calculator section, part B of the free response questions, section 2 of the AP Calculus BC exam. Thank you everyone for watching. If you have enjoyed this, then please do check out the rest of the exam playlist. There are at least 10 other videos you can watch of me struggling my way through high school maths exams. And of course, please do remember to subscribe to the channel. I'll see you all very soon. Take care.